subject is material science. The knowledge of material science is essential for a designer because what kind of material is having the melting point or the hot working or cold working. So these are the very essential amount of knowledge that is required for a designer. That means if a member is working in elevated temperatures and it's a red hot condition, that means the recrystallization temperature is equal to the working condition, then the member is going to change in the plastic manner. That means the deformation is going to take place in the plastic manner. So therefore, the knowledge of the recrystallization temperature, the knowledge of melting point of various materials, metals or non-metals or alloys is also essential for a designer. Now, let us talk about how you are going to design an element or a member. A member or element. The design is either we are going to determine the dimensions of the member or we are going to determine the maximum amount of load it can carry before failure occurs. Before the member is subjected to failure, the dimensions or the maximum load it is going to carry are determined. Suppose if we have taken a bar, this bar is subjected to a pull P and its cross-sectional area is small a, then the stress developed in the member is equal to load upon the area. If the stress developed in the member or induced stress is equal to the ultimate stress sigma ut, or in some other books it is known as SUT. The induced stress is equal to the ultimate stress, then it is the condition of failure. That means this is the maximum amount of load the member is going to have, or this is the minimum amount of cross section the member is going to have. Either we determine the load P that is equal to sigma, that is induced stress is same as sigma ut into the cross sectional area R. In other words, if you want to find out the area A, then that is equal to load applied by the stress. So R SUT, because the design condition is the induced stress is equal to the ultimate stress of the material. So by the way, either we are going to find out the maximum load the member is going to carry or the minimum cross-sectional area of the member on which the member is subjected to this much load, but it is not going to fail. So if this area is, let us say, 2 bars, there is a bar 1 of diameter D1, there is another bar of diameter D2. Both are subjected to a tensile load. Here from the diagram we can very clearly identify that D2 is greater than D1. But both are made of same material. That means the SUT or the sigma ut is same. But D2 is greater than D1. Therefore, the load carrying capacity of the first one P1 is equal to the SUT or sigma ut into the area. So here the area of the first one is smaller and the area of the second one is greater. Since A2 is greater than A1, this P2, that is the load carrying capacity of the second bar, will always be higher. Both are made of same material, but second one is having greater cross-sectional area, therefore it is going to have greater amount of load carrying capacity. Now, we may talk about what is failure. As in the earlier part of the discussion, we said before failure, what is the maximum amount of load it can carry? That is the failure point. Then, let us talk in detail about the failure. Failure is a member subjected to any of the 5 types of loads discussed in the first part of the lecture. If this load is applied, the member, according to MOS, it is deformable. The member is deformable. But if you are increasing the load starting from 0 to some maximum value, if you are increasing this pull from 0 to some maximum value, by the way, the member is going to stretch. To certain extent, the member is going to extend elastically. That means when the load is removed, it can come back to its original state. That is called elastic zone, or the elastic limit is the stress up to which the member can be loaded. So until that point of load, the member will be in the elastic zone. That means it is going to stretch in the elastic manner. But beyond that, what is going to happen? The member is going to permanently deform. The member is going to permanently deform. The permanent deformation is known as failure. The permanent deformation is known as failure. Therefore, the ultimate stress, or SUD, which is known, is applied with some factor of safety, FOS, factor of safety. The ultimate stress or maximum stress for a particular material, which was determined in the laboratory test by using UTM, and applied with suitable factor of safety, we will get a stress value. This is known as allowable stress. Allowable or working stress. The allowable or working stress is generally used to determine the dimensions or load carrying capacity or safe load carrying capacity of the member. Now we are going to modify the earlier thing. So the allowable stress is taken for the design. This is equal to load applied P upon the cross-sectional area of the member. If you want to determine the cross-sectional area of the member, then A is equal to P by sigma allowable stress. So if load is known, that means this member has to withstand 2 tons of load. That means load is fixed. But what is changing? The changing is the cross-section area. You can change the cross-section area so that the member is going to withstand 2 tons of load, and it is made of certain material. Let us say it should be made of mild steel. So mild steel is having so much the ultimate stress. For the bar, you are applying a factor of safety of 2. Then SUT by factor of safety will give us allowable stress. The allowable stress is taken in the denominator, and in the numerator the load applied 2 tons. Based on these two, we are going to have A. That is, if the member is circular in cross section, this A is equal to pi by 4 d square, and from this we are going to find out the diameter of the bar, which is subjected to axial tension. Next, we have theories of failure. We may call theories of elastic failure. There are totally 5 theories of failure, but popularly 3 theories of failures are used. The first one is maximum principal stress theory. Second one is maximum shear stress theory. And third one is von Mises theory. The first one is suitable for the brittle material, and the second one is suitable for ductile material, and the third one is suitable for mostly ductile material, but it can also be taken from the brittle material. So this is also for ductile. So based upon the complexity of the loading, based upon the accuracy of stresses we are going to determine, and the more precise values of the dimensions needed, we go for the von Mises theory. But in general, either we go for the principal stress theory or maximum shear stress theory. Member is made of ductile material, we go for maximum shear stress theory, and member is made of brittle material, we go for maximum principal stress theory. So in the maximum principal stress theory, we take the sigma ut is equal to the sigma, that means induced stress. The induced stress is equal to ultimate stress. But as we have seen, we are applying some suitable factor of safety. Therefore, sigma ut by factor of safety is equal to sigma induced. That means when the member is subjected to some axial kind of loading, then there will be stress that is known as induced stress. This induced stress is equal to material's failure value, ultimate stress upon the factor of safety. So from this we are using the maximum principal stress theory for the brittle material. Next, shear stress theory. The shear stress theory, tau ut by factor of safety is equal to tau induced. So when the member is subjected to a tangential load or torsional load, there will be shear stress induced in the member. That induced shear stress should be equal to the ultimate shear stress upon the factor of safety. The factor of safety is taken as